from my side, and welcome to our webinar series Rutronik Connects. We are already in our third week of our webinar series Rutronik Connects. The first week was all about Wi-Fi. The second week was all about cellular and GNSS. And this week we have ultra-wideband, LoRa, and some other technologies. Today I want to welcome our highly appreciated partner, Yageo Pulse, with their theme, Innovative Antenna Solution for Wireless Communication. Experts discuss LoRa and ultra-wideband technologies. Here again, you can see me, and I want to welcome our two speakers of today's session, Gregory and Kimmo. Welcome to you.
Thank you.
First of all, some practicalities. The duration of our webinar will be around 1 hour. Questions are, of course, welcome. You can type them on the right sidebar in the Q&A. And we will answer your questions at the end of our webinar. If you have further questions, of course, you can ask us and we will answer them also afterwards. The presentation and the slides will be recorded, and also with the presentation of our presenters, you will receive them afterwards. So again, hi, Gregory and Kimmo, and I will hand over to you both, and you can start your presentation. Have fun, everyone.
Thank you again, Tobias, and the whole Rutronik team for giving us this opportunity to present some of our technologies and give a little bit of an explanation for why a designing engineer would choose to design in a LoRa or ultra-wideband radio and antenna in their product. As Tobias mentioned, my name is Gregory. I'm located in Washington State. We'll see a little later on some of our manufacturing locations, including where Kimmo and myself are located. And so this presentation isn't going to be exclusively LoRa and ultra-wideband, although we're going to focus on that, certainly. I'm going to begin first by giving, next slide, there we go. I'm going to begin first by giving a little introduction to what Pulse Electronics and the Yageo Group, we're a member of the Yageo Group, what it offers from a wireless point of view, our wireless product portfolio, both from an RF protocol point of view and from the mechanical solutions and options that we have. And then we'll jump into, what is LoRa? Why would you choose LoRa? And after that, ultra-wideband. So briefly first, we like to break down the categories of products we have from an RF point of view into 4 different sort of market segments. You can see here the mobile devices segment, the IoT segment, the infrastructure segment, and transportation. Now, briefly, of course, you might think, well, where does LoRa and ultra-wideband fit into these categories? I would say that, certainly they can find places in almost all of these market segments. Perhaps I see LoRa most often in IoT and infrastructure, and I probably see ultra-wideband more often in mobile devices, transportation, and somewhat in IoT as well. So just a brief, point there. Now, there are different design considerations, different design challenges that we run into and face for these different market segments. For example, mobile devices require designing antennas into components or end products that have a lot of metal, that have LCD screens that are issues for antennas, things like this, and require cellular bands. You've probably heard about cellular last week or the week before. That has a lot of different bands, especially for designing for 5G. So long wavelengths in a tight device like this become hard to design for. Whereas for something like infrastructure, we often are allowed more space for an antenna. Going to use larger antennas maybe that are visible to the naked eye from somebody on the outside. So we have different product categories we target for these different market segments, and they have different characteristics typically that the antenna needs to meet in order to be successful in that market segment. Now below that, you'll see the wireless technologies. I don't know if my mouse shows up. I hope it does, but below that, you'll see the wireless technologies that we service as well. You'll see cellular bands. You'll see Wi-Fi and BLE. You'll even see GPS and other global navigation bands like Galileo. And then you'll see RFID, NFC, but here we have LoRa, long range, and ultra wideband UWB technologies. So certainly we include these technologies in our product lines. That's why we'll talk about them today. Those were kind of the RF point of view. Now, what kind of form factors might these antennas take? And the next few slides will also describe some of the benefits and downsides of different mechanical topologies you can choose for your antenna. But briefly, you can see here, for example, our product line covers everything from the PCBA mount and type antennas, those you'd solder directly to your PCB, both ceramic chips, ceramic patches, helical, stamped metal, all kinds of what we call embedded antennas. What we call 3D antennas, those that are going to be on a plastic surface, typically either plated using plating technology or printed using a printing technology, think of it like an inkjet printer, directly onto a plastic piece, perhaps the housing, perhaps a separate plastic piece of the antenna, often customized. Internal antennas also inside a housing, but not directly mounted on the PCB itself and not a part of plastic, as it were. These are separate flex materials you'll place inside the device. External antennas now are visible to the outside world. We're no longer inside the housing of the device. And then we go into outdoor antennas, perhaps, if I skip a little bit down to the outdoor antenna category, where these are going to certainly need to be IP rated, IP67. The external antennas maybe don't have to be. Maybe they're on a gateway or a router, for example, and it's going to be indoors, but these outdoor antennas certainly will need to be IP rated, and maybe the plastic needs to be UV resistant, things like this. Vehicular antennas that are designed to mount on vehicular rooftops and have sometimes many antennas in one housing with multiple cables to reach those. And the cable mounts and assemblies, certainly we support making sure the antenna, the signal between the radio and the antenna can be made across analog paths. And then I sort of skipped over RF components. We probably won't spend any time talking about these RF components today, but for example, you could utilize bandpass filters. For let's say an ultra wideband product, you might use a bandpass filter to eliminate any noise between on the board from some other sources. So you might place that in line between the radio and the antenna. With LoRa and ultra wideband, you are unlikely to be utilizing something like a diplexer, for example, but a filter and possibly a balun would certainly be options you might consider. I did mention that I talk about our footprint and just to showcase where we're located. Kimmo is much nearer. He's located in Finland, Oulu. So he's not too far away, and he's our head of research development in infrastructure departments. I'm located in, I mentioned, Washington State, a city called Vancouver, Washington, on the west coast of the United States of America. So typically I'll support the Americas. And you can see here we have manufacturing, not in EMEA at all, not in Europe at all, unfortunately, but we have manufacturing both in the U.S. and Asia. Probably no surprise there. Okay, so I'll be going over in the next few slides, different types of antennas mechanically again, and what some of the benefits are, or why you would choose a certain technology maybe for a certain application. But first, let's dive into what is LoRa, and I've used the longer name a couple times already. LoRa essentially is just short for long range, so maybe not too crazy, but easy to remember, I hope. And that's kind of what its main purpose is. LoRa is about 10 years old now, actually, so it's just coming along its decade of existence, as it were. Really, 2015 was kind of the true, you could say, launch, I would say, but to 2014 it was really developed. And so the goal for LoRa is to allow you to communicate over a large distance. And it accomplishes in a couple different ways. One way is it's got extremely high sensitivity on the radio side, down to negative 140 dBm. It's certainly possible with some radios. So you can have extremely high sensitivity. So even though the signal has, attenuated, it's traveled over distance, still it can be picked up and the data received. So that's one of the key methods in which it allows for that larger distance, and we do mean kilometers of distance. Absolutely, 10 is not unheard of, and especially in a rural environment, and in possibly even longer than 10 kilometers. One other benefit, I would say, you could call it a benefit anyway, for LoRa, it uses an unlicensed frequency spectrum. For example, you're not paying a cellular company, a carrier, to utilize a band. It uses what's called the ISM band, and that stands for Industrial, Scientific, and Medical. And we will sometimes use these terms interchangeably, which isn't quite fair. There are other technologies that use the ISM band, so we shouldn't use them too interchangeably. But LoRa, of course, is a big player using this frequency spectrum, especially as we'll see a certain chunk of that frequency spectrum, and we'll look at that spectrum. But so that's the band it uses, and so you don't have to worry about any kind of fees for using that frequency spectrum, as it were. One other big benefit of LoRa is that it uses relatively low power radios. So, a very small battery, like a coin cell battery, can survive for years powering a simple LoRa using device. Many years on just that, because the low power radio, both in the receive and transmit case, doesn't use a lot of power. So that's another big benefit to LoRa technology. Of course, just one downside, I guess you can call it a downside. One aspect to keep in mind with these benefits, especially things like low power, expect that it does come with a lower data rate. We're talking, kilobits per second. So if you need to transmit video signal, for example, you're not going to use LoRa technologies, not necessarily for that application. It can be great for small amounts of data, and we'll talk about later. It can be even good for determining the device is offline. So the frequency spectrum, that LoRa will utilize. We have here on the left some of these bands. The key ones I would point out are the EU band surrounding what we say 868 megahertz, and the US band, and these two bands, of course, are used elsewhere than just the EU and the US. They kind of using them earlier on, of 902 to 928 megahertz, or as we call it, centered on 915 megahertz. These are the most largely used spectrums, I would say, for LoRa and for ISM technologies in general that are outside of the 2.4 gigahertz band, which is also an ISM band. So these are, where we'll find a very large selection, both from a radio point of view and from an antenna point of view, for example. But you'll certainly also have selections if you're looking to design, for example, 433 megahertz in the EU. There's certainly opportunities both from a radio and antenna point of view, and in some cases that offer you can utilize both bands. So these are the sub gigahertz, then the term used typically for technologies that are these ISM bands, including LoRa. It's below the 1 gigahertz point. These frequencies, you'll see them 868, 915, 433, and then some other technologies to utilize other bands there as well. So these are, I would say, you'll see, especially at the time speaking to LoRa, you'll see especially some 915 megahertz technologies that are, products and stuff I'm familiar with our customer base, applications I'm familiar with the customer base here in North America. But you'll also see, a lot of 868 options in our portfolio, as it were. That's another commonly used band for EU designs, and of course those frequencies aren't so far apart that a lot of antennas that are designed to cover both. So it can be utilized in both regions, a single SKU, as it were. There are certainly options to utilize that. So this page has a lot of products, and many of them we're not going to notice specifically for LoRa application. You'll see here on the right this 800, 900 megahertz spectrum. That's especially, spectrum as mentioned above, that we can utilize for LoRa. So some of these products, some off-the-shelf, catalog options that will cover either 868 or 915, for example, or both in some cases. But they're not exclusively the only products that do that. Another thing to keep in mind is that cellular antennas also catch those bands, as it were, that frequency spectrum in their coverage. Typically, a cellular antenna will be designed starting at frequencies below 863. If it's a 5G antenna, for example, it'll start at 617 very often. It'll go through 960 megahertz, so it'll go above the 915 megahertz spectrum. So cellular antennas often also can be utilized for LoRa applications. So you'll see some antennas here in the cellular category that can be utilized. In this category, these outdoor antennas, we actually have a product here, the RO31SMNM. Stumbled on that a little bit. That covers both 433 megahertz and the 800 megahertz spectrum for LoRa. So it's actually you can call that a dual band EU spectrum antenna. So what are some of the benefits of an outdoor antenna, or what are some of the applications you might utilize it for? Now, obviously, the benefit is it's IP rated. It's going to be something that will survive the rugged, use in the outdoors, the elements, sunlight over time, rain over time, etc. Will be wind load tests done on many of these antennas. You can see, of course, they're quite vertical, so you need some wind load testing done. Now, they're more expensive, so it's the downside to them. So you really want to utilize them or design them in when you need to use them. Perhaps it's a rural application, and you have to have an outdoor antenna. Maybe it's on some tractor or something, or something that you want to have some data on in a rural application. Maybe it's a base station being utilized in an application that is receiving from many different transmitters in a farm field. So, focus a little bit on agricultural there, but that's maybe where you'd want to design these outdoor antennas. They're key when you need something that's going to survive long term in the outdoors, but they're expensive. So you only want to design them in when you have to. But the product portfolio is certainly there. If you don't need something that's very rugged, very IP rated, but maybe you're in an industrial setting, for example, in a factory type setting. So you have maybe it's a metal box with sensors inside, and so the metal box, of course, will block any kind of signal from an antenna that's inside the box. So you need some kind of external antenna, something that you would have seen historically on a gateway or a router. That's why you perhaps would use an external antenna. You can think as a simple rule of thumb, as a word, typically a larger antenna or one that has more space for itself can perform better. There's, of course, you can call it diminishing returns. There's a limit to that. Antennas have a limit to their performance, but you can think of that as these are typically going to perform better than an internal antenna. So another reason you might utilize them if you're not concerned about the aesthetics, as it were, if you don't need to worry about the end user seeing the antenna. Again, factory settings is a good example of that, or other infrastructure settings. Certainly, it could be lighting setting, for example, on a light. So we've again showcased some products here. You can see here we've titled it sub-gigahertz ISM instead of the 800, 900 megahertz. Different terminologies that are looking at the same end application. In this case, some of the previous antennas on the other page had usually N connectors, or in some cases maybe an NMO connector if it was meant for a base station with a vehicle type setting or an NMO mount, but often N connectors. For these external antennas, you'll have most commonly RP-SMA connectors with LoRa technology, but also SMA connectors. You'll see both. See a variety of shapes. Typically they're not IP rated. Some of these are IP rated. The W1063 has, for example, a bending joint, an articulating joint here. Others do not have that, which makes it easier to make them IP than just a vertically mounted antenna with a connector at the bottom. So a variety of options there. And of course, again, cellular antennas also will work for the sub-gigahertz band if you are not focused on increasing the gain of your antenna. Typically, cellular antenna is probably not designed to have greater than 2 dBi on that band, whereas a LoRa focused antenna might have 5 dBi if it's really large and really focused antenna, especially a base station. So internal antennas, if you need to have it, or if your device especially is going to have consumers using it or end users who, you have an aesthetic, a marketing point of view to keep in mind, then you'll often not want to use an external antenna. You might use an internal antenna, a flexible antenna with cable, like these products here. You have a variety of these, but typically they'll not be rigid. They do have some rigid options. They'll typically be flexible with cable length connector types that can be modified. Of course, some of the most common ones are the MHF1 do-not-fail type. Again, some products in this category. The W3312 will actually see an application in another couple of slides. Newer products from our line include these SWA 4359s and 4389s that are half the size of the W3312, which really acts like you could say like a dipole. So for high performance, and these ones a little bit, they're half the size, have good performance, not as good performance, but so another, why would you use these then maybe instead of an embedded antenna? Well, maybe there's shielding around the PCB. So an embedded antenna is blocked by the shielding, or maybe there's a battery underneath the PCB, which is going to reduce the performance of the embedded antenna. So sometimes you need to get the antenna further away from the radio, not because you necessarily want to, but just because from an RF point of view, you have to get strong performance. So that's a common reason to choose an internal antenna with a kind of user device that still needs to hide the antenna, as it were. And we'll see that, or maybe it's something where if the antenna were external, it could get damaged. We'll see that with a sprayer example later on. And also finally, I alluded to the embedded antennas for ISM, for LoRa. So you would utilize these if you can. Really, I would say honestly, this is probably your first goal because they're the least expensive. We all have costs to worry about. And if you have a large enough PCB ground plane, they can perform very well. That's the downside to these, and we'll see in the next slide. You have to worry about the size of your ground plane for designing in these products. So they do have some technical challenges to them from a design point of view. But if they can perform to their best, they're inexpensive. So they're going to be mounted directly on the PCB as a part of your SMT process. So a lot of benefits of these, antennas. Excuse me. For example, I think the title is wrong here. It says GNSS, but these 4 antennas here are LoRa type antennas. The W3015L actually is a 433 megahertz antenna. So one of the few, down to that frequency, it's a helical type antenna. We have a vertical helical antenna for 915 megahertz. We have a simple ceramic chip for 868 megahertz in EU. W3136 is a helical that covers both bands, so you can utilize it in a single SKU for both the EU band and the North America band. So a variety of products there. And then in the combo section, for example, the W3320 actually has a port for the 868 915 megahertz and a port for 2.4 gigahertz, which is also an ISM band, but LoRa doesn't utilize it. But for example, if you needed a Bluetooth and a LoRa, if you have a radio for Bluetooth and a radio for LoRa, the W3320 can be an excellent product to knock both of those out at the same time. And that was an example of products we've had under the Pulse brand name for a long time. We do have newer products using a technology, low temperature co-fired ceramic technology, that we didn't have until recently. Those are all high temperature ceramic products. The difference is these are often corner type monopoles. You can see here these 870 and 915 megahertz. They call them 870 for the 868 band. They're monopole types at the corner instead of an edge mount like the other, a couple of the other ones, where a monopole type an embedded antenna really cares about the ground plane in front of the antenna. And again, I mentioned that for an embedded antenna, you do need to worry about your PCB. So I would recommend, if you're designing one of these products, have the company, for example, if you're designing one of our products, ask us to review your layout, provide us the Gerber files. We'll review your layout for free to see if we see any issues or concerns with performance. It really, the PCB copper pore is key to performance. The edge mount antennas, for example, if they are, for example, the W3013, they rely on the current traveling around the keep out area of the antenna for bandwidth and for resonance of the antenna. They rely on the total perimeter of the antenna, the PCB, the copper pore, for radiation performance, for higher efficiency, for getting maximum radiation instead of being cut down due to the smaller ground plane. So these aspects do matter. Whether the keep out area is proper, whether the feed line is proper. So there's design challenges to an embedded antenna, but certainly, of course, if you can, they're less expensive, and we recommend them where you can design them in. I'd like to take the next few slides to talk about a few different antennas and especially case examples. I can't go into too many details about customer side of things, but you can see here one of the helical antennas, the W3136, I called it out a couple pages ago on the embedded slides, designed into a product where you can see it's plastic beneath it. There are 2 screws next to it, but being a larger volume helical antenna, it's not as impacted by some of that metal nearby. Certainly there's still an impact. Antennas, as you imagine, don't love metal nearby, but it's the monopole type antenna really with the helical design. And you can see here, these are data sheet performances, but it's a high efficiency antenna across that whole spectrum. So, this could be mounted on a wall somewhere in a home. Could be for sending sensor data throughout a home, for example. And of course, this really allows you to utilize this both in North America and in the EU or elsewhere that utilizes the 915 and the 868 megahertz spectrum. It allows you to have a single, there are radios that allow for both. So it allows you to cover all of your, well, most of your bases of the word. That's really going to have almost universal deployment coverage capabilities there. So it's a great product as long as you have, again, some vertical space, for example. That's really probably the challenge most often run into with antenna is the vertical space. And of course, you need enough ground plane space in front of the antenna, being an embedded monopole, in order to get peak performance. But if you have the space for the device, this is an excellent, in-building install for LoRa performance. And you don't always need to utilize LoRa for, a long range, as it were, as it's described. It can also be, utilized for its low power needs if you're only sending small amounts of data, right? Sometimes you may not need it to go extremely long distances, but, maybe you would want to keep track of things like doors in a building. We've seen you can utilize LoRa on smart doors, doors with electronic components for tracking if doors are open, etc. This is a more specific example where, well, again, we're able to show a little bit more here of the antenna side of things. That's a customized printed antenna. We talked about very briefly how we have those printed antennas. So this is just printed with silver ink. You can see that this device has more than one antenna. It has a 915 megahertz for LoRa use, it has a Wi-Fi and a GNSS as well. Now this is a cow ear tag. So it's essentially asset tracking. In this case, tracking of livestock, cows in this case. In this case, of course, saying what data am I getting from tracking the cow? What's the sensory data? Well, actually, you can utilize LoRa as well, essentially as a location finder. So with LoRa allows itself to act. Think of it as multiple gateways, the different LoRa devices. So you can pinpoint utilizing other LoRa gateways the location of an object or an asset you're tracking with 915 megahertz. So you can use it as an alternative to GPS, and that might be valuable in a case where you have example something like an animal like a cow and your tracker here is going to be moving around a lot. Now this GNSS antenna is not designed as a directional patch. Obviously a directional patch doesn't make a lot of sense on a cow. It's very hard to imagine where you can install a directional patch that would always be facing the satellites. But even so, it's designed to be a vertically polarized simple monopole, or well, really a PIFA. It still has its limitations, whereas this long-range 915 megahertz band may allow you to see where the animal is in cases where GPS has failed you. So it makes for a good alternative in some cases to GPS. So this kind of use of LoRa is also something we'll see in rural applications. We couldn't show everything, of course, related to this one either. This is a customer who does lighting, especially here in North America, but they utilize more than one of our 915 megahertz antennas for tracking some limited data, but also to see if a lighting has failed, if a device has failed. I mentioned again, sort of that they can act also as gateways. When the signal stops from a 915 megahertz radio, you can tell that something has failed there, right? So these are also paired with Bluetooth and BLE in these devices for data tracking, especially BLE used when the service technician comes up to the light for tracking certain bits of data tracked by the sensors inside the light. But that low data, not very heavy in data, the sensors are picking up inside the light can be transferred very easily over 915 megahertz as well. If you're doing something that takes high data like video, this would not be a good application for that. But if you are just sending simple sensory data, then the 915 megahertz spectrum LoRa is a great technology for it. So this is great as part of a larger network as well to see. Again, I mentioned you can tell if something has gone offline, if it's failing to send information anymore. Very easy to see that with these networks. So the 3312 I mentioned earlier is shown here. It's utilized in a couple different ways by this company. Also, is an example of an antenna that we didn't showcase earlier, but is in our catalog, the W9019. It's a NiTi wire. The little NiTi wire can bend very easily inside a device, but it's got it's flexible in that regard, but it's not going to break very easily either. It's not simply just going to snap on you or break, and it can connect the same way as one of these antennas do to that typical MHF1 UFL type connector. There's another application for infrastructure type projects, and we'll see a variety of infrastructure used with LoRa. We'll see it in metering companies, sometimes as low as to the ground as like in the earth, as it were, on a manhole cover, say, or a lid, for transferring data utilizing LoRa 915 megahertz. It allows people to collect data without having to go to a meter to read the meter's data. Or utilizing other infrastructure projects. This is a lighting application again, where in this case, this antenna is designed to not just be the 915 megahertz LoRa spectrum, but also the Wi-Fi spectrum. So the single antenna can perform both at 915 megahertz and at 2.4 gigahertz and 5 gigahertz. In this case, up to the 7 gigahertz, including including that 6 gigahertz spectrum of Wi-Fi 6E, for example. So it's a good, metal mount solution. You can see here it's relatively small form factor and still can accomplish that longer wavelength. So it makes it an effective solution for if you have a radio, or you can of course have a diplexer or triplexer, and have a single antenna on a metal surface covering all these bands. Excellent for infrastructure and rural use cases, especially. So I realize now, especially this is my last example, I believe. I don't have as many urban examples, but we do see these. I mentioned, doors, for example, electronic doors. You'll see them utilized as a backup plan in fall alert devices. We have products signed in there. So absolutely, you'll see LoRa used in an urban environment too, because and I haven't, focused on the definition of, for example, wavelength so much, but it's a longer wavelength than some other technologies like Bluetooth, for example. Bluetooth using 2.4 gigahertz, LoRa using 915 megahertz. You have a longer wavelength, so not only is your radio very receptive, very sensitive, but also the signal doesn't attenuate nearly as much when traveling through walls in a building, for example. So there are certainly values in an urban environment. I apologize, I did not include more examples of an urban environment. We perhaps should have done that, but that longer wavelength has its values in both in almost all use cases. That fact the signal can travel further without it attenuating so much, through structures as well as just over the Earth's surface. So even in an urban environment, you can get a kilometer out of LoRa technology, which is great. So I mentioned before, of course, it's kind of a summing up, a review of the different benefits of LoRa, which is why I had that little tangent. And this is a final, final example case, and this actually is going to be the little, you can call it the nozzle, the sprayer here, a backpack sprayer you could utilize for spraying pesticides or for spraying water on surfaces for cleaning purposes, or the variety of purposes one of these little backpack sprayers might utilize. And you can see here a GNSS antenna, you can see an NFC antenna. Now I've had to cover up some of this, device here internally, but you can see right here there would be a sub-gigahertz antenna, but actually here is a sub-gigahertz antenna hanging here. It's a little flex of cable. So even though you have GPS, this is also that's for positioning. This can help for positioning if the nozzle is not currently facing the sky, but also this is utilized for data transfer. It can be utilized both for sensors and actuators. If you need it for actuators, it wouldn't need it in this case, but could be utilized in that case as well, because again, this is a pretty low amount of data rate to describe what's happened. And again, why is this popular compared in a lot of cases to cellular? Cellular also has some long wavelengths that allow for quite a bit of transfer or distance travel, and I would say cellular is key. If you have to have something that's always on, perhaps cellular might be something you consider for those kind of applications. But that has a carrier fee involved, right? There are fees involved to using cellular service. You can have a kind of a private network using LoRa without having to worry about those fees. And we talked about the long line of sight, the long range you can accomplish utilizing LoRa technology. Again, it also is still very good in an urban environment. Travels a long way through surfaces and things like this. I have a good note for that. It doesn't attenuate like Bluetooth does through walls and things like that. So there's certainly some benefits for LoRa technologies. And I believe that is the end of LoRa, and I'll be passing it off to Kimmo.
Okay, thank you, Gregory. Let me try to take a control of this PPT. Maybe not. Okay, so you need to switch the slides for me. That's fine. Okay, so next we will talk about the ultra wideband, and the main focus will be maybe showing more applications and examples for you to get an idea for typical design cases where we have been implementing the ultra wideband. So there will be different categories for those examples, different product styles. And I will show a couple of examples of our catalog part offering to using different antenna manufacturing techniques. Maybe one good point that you will see on these slides is that quite often to get optimal performance for the UWB, you need to use a customized solution, or at least do some very precise tuning for these antennas. And the reason for that is that it's a pretty high frequency application, typically 6 to 10 gigahertz range often, and the wavelength is getting so short that when implementing these antennas onto the device, all the mechanics and other components around the assembly, they have a big impact on the final performance and tuning. So that's why some design challenges occur, and optimizing all the things often leads to some customized or semi-customized solution. Okay, next slide, please. I will talk in more detail about these cases, but already here you can see couple of very different style antennas implementation. On the left side is an example of a real smartwatch case with metallic housing, and all these antennas are 100% customized to that device. To make something work in a very tiny device with metal enclosure, it's really quite hard to use something off the shelf. But I will get in more detail on this design case later. Right-hand side of the slide, there's an example of the array antenna for 7 to 8 gigahertz. And this is actually a off-the-shelf style antenna, and it's realized in the two-sided PCB with pigtail feeding. And of course, the meaning of array is that it can have a higher gain and directional pattern instead of being a omni style. But also more about this kind of application in coming slides. So next one, please. So here is one example of the off-the-shelf LTCC style chip antenna. Maybe it's good to mention also that the majority of these design cases example is focusing on the higher end of the UWB frequency, typically from between 6 to 10 gigahertz. Often people don't remember or realize that the actual UWB standard starts from 400 megahertz, 4 to 500 megahertz area. If using a antenna on that lower frequency spectrum, it's quite usable to take some of the ISM band designs, for example, some helical antenna or something else that is designed for that 4 to 500 megahertz area and tune that to work on the exact UWB band. Then there is also the UWB spectrum from 3.1 gigahertz, between 3 to 6 gigahertz roughly. And past several years, we haven't seen so many applications using that spectrum. So that is the reason most of the examples here they are focusing something 6 gigahertz and upwards. And for those 6 to 10 gigahertz area, we have a few off-the-shelf parts available. This LTCC one is the first one presenting here. And really, it's quite similar antenna, monopole chip antenna that are used on the lower frequencies, just tuned and matched for wider bandwidth. And the same design challenges apply here as Gregory mentioned. The device PCB ground plane size is very crucial. But thanks to the higher frequency comparing to the, for example, LoRa 900 megahertz, this can work with much smaller ground planes than those low frequency antennas. So everything when designing an embedded or internal antenna is related to the wavelength and the size of the device. So those are a couple of key things to keep in mind when designing in embedded antenna. Next page, please. This is also similar as the previous one. This is PCB mount monopole, but not using the low temperature co-fired ceramic, but so-called HTC, which is the high temperature version. And the key benefits here comparing to the previous one, they are actually the same size antenna chip, but this one is optimized for using a smaller keep-out area. And thanks to the matching circuit that is designed onto the PCB, it can cover wider frequency range up to 9.2 gigahertz, so up to channel 12. This is also good comparison and good to keep in mind that even though the antenna chip size is same, it's not only the, let's say, the ceramic body size that defines the antenna performance, but also the layout and possible used matching circuits. Those can be a big player when thinking about how to optimize the performance and what kind of bandwidth, for example, can be achieved. Right, going forward, other styles. Yes, next page, please. FPC style antenna. Key benefit here comparing to board mount chip antennas is that they are more immune to ground plane sizes, as the antenna itself works as an individual radiator. And thanks to the fact that the wavelength here at the 6 to 10 gigahertz, it's very short, so it's possible to design a dipole style radiator and still keep quite small dimension for the radiator. So this times 16 by 5 millimeters only, and you can have a very insensitive antenna so that the ground plane size or device box doesn't much affect to the antenna performance, of course, given that it's put inside a plastic enclosure. Next one, please. Yet here's another version. This is a slightly bigger radiator size. Main reason for doing is that we can slightly get the better stability for the DSWR and even wider bandwidth. So practically it goes over 10 gigahertz, covering the full UWB spectrum. So here also the size matters. Typically, the bigger aperture you get to the antenna, more bandwidth you get. But of course, again, there is no need to kind of over-design the antenna. So if you are using only some limited or selected channels on UWB, you can or better to choose the antenna so that it's optimized for that spectrum and not necessarily covering all other frequencies. Okay, next one, please. Here is an example of a customized UWB antenna to a smartphone or cell phone. This is using like a 3-element flexible PCB. So it's quite obvious to imagine that something like this you cannot get off the shelf because everything is matched to the mechanics of the device and tuned for the mechanics of the device. It's more like showing the design capability that if there is a need for customized solution, we can do that. And the other example on the right-hand side, it's like a small tag. And this is an example of the printed antennas, like Gregory showed the example of this cow ear tracker for the LoRa. It's similar to manufacturing technology. We are using that for many frequencies. In this case, there is actually an NFC coil in the middle and then the tiny UWB radiator at the side. again, maybe more like an example of the design and manufacturing capability. Next one, please. Here are some measured and simulated performance metrics of this kind of customized cell phone antenna. And you can see here that it's because of the environment, it's sitting on top of the LCD screen, which is one big design challenge on these highly integrated devices. The resonances from the antenna, they are very, very narrow, and it's definitely not covering all the UWB channels. So it's designed for those channels only that are used for this particular cell phone type. While we, on those catalog antenna examples I showed, we saw very broad response covering all channels. This is nothing like that. This is very specified to the selected channels only. Next one, please. And here are some more like design iteration graphs, just showing that with tiny changes on the radiator, we can tune those resonances to a desired band. So that's part of the custom design process to work through variations and find the optimal solution for each case. Next one, please. Here is more about that smartwatch design. So the actual application on this case is to kind of detect the position where you are moving, for example, inside a building. And the two bottom graphs here are examples, so that well, bottom left is when you are like an open corridor, lot of free space, you can get something like 20 meters distance for your UWB tracking or location. Right-hand side bottom, that's the like a crowded office environment and a lot of disturbance due to environment. The detection distance drops to 9 meters. So like a half of the range comparing to the more open space. And one also important finding on the top right graph is that this is like a body-worn device what's used on the human wrist. So we need to take into account the detuning by the body tissue, and also realize that there is so-called hand loss or body loss effect, several dB performance reduction comparing when the device is used in a free space without body loading, and then it's worn in a real application. So this is maybe a message or one design challenge that if the end device is used on such environment that there is like a loading effect from body or some other material, wall or something like that, it needs to be taken into consideration from the very beginning of the design cycle. So understanding how and where the device is used is very key, practically for any kind of antenna application. So you cannot just choose your antenna based on some like datasheet numbers or stuff like that. So you need to think about the final application and then work through the design iterations based on that. Okay, next one, please. Here's an example of you actually using the off-the-shelf antenna in a quite small device like a key fob for like a car remote control or something like that. And also showing that by utilizing the simulation tools, we can get quite accurate presentation of the real antenna performance, matching the VSWR and seeing the radiation patterns, hand effect, that kind of things. So that's part of our design capabilities. Next one, please. Here is quite interesting application using a UWB to detect humans or live matter inside a vehicle. I think the picture tells a lot why and how this may be used. So the idea is to detect if there's some humans inside the vehicle, and we shall not detect anybody outside the car. So it could be like a security application or that kind of thing. And we first tried to use this kind of more like omnidirectional antenna. In this case, the problem was that because the gain of the antenna, it was pretty much equal to all directions. It could detect both the people inside and outside of the car, and it didn't work. So we really need to go to the directional antenna. And I think next page is showing. Next slide, please, Gregory. Yeah, this is showing how with an array design we can do a directional pattern, so we can minimize the antenna gain and radiation to all other directions, but to the desired main beam direction. And something like 3 to 4 dBi gain can be achieved on these 6, 7 to 8 gigahertz frequencies. Again, this is a good example that you really need to understand how you will be using the antenna, how it needs to be optimized so that it meets the requirements on that specific application. Next one, which I believe will be the last example. Again, quite unique application. This is a solar cell panel array on the building rooftop. And the use case here is such that the UWB is used to communication between the solar cells, different panels. And important matter here was that the radiation pattern of the antenna needs to be as omni as possible on the plane of the solar cell, so that we can get the equal signal from panel to panel. You can imagine that if there's a big array of panels, tens or maybe hundreds of panels next to each other, and we want to communicate, kind of make a mesh network, it's very important to have a like omni gain and omni pattern from the antenna, as well as some other important parameter is the group delay on the ultra wideband signal processing. Group delay is one of the key parameters, so it needs to be as stable as possible, so that the signal is not distorted when looking for different directions. So we have a capability of simulating and measuring the group delay if needed. So that's one parameter to follow on this UWB cases, especially when there are multiple antennas used, and they need to be behaving as equally as possible. Yeah, I think that was my last example slide on this one, and the idea was to show that in how the antennas can be used and what kind of applications we have been working with the last couple of years. So quite different ways to use the antenna and why it is used. Okay, I think that's for the presentation. Tobias, we can take it back to you.
Yeah, thank you very much, both of you. Amazing presentation and information. We do have some questions already. I would jump straight into the Q&A session. The first question is, it looks like many of your ultra-wideband products are customized. Do you always charge an NRE for ultra-wideband development?
Okay, I can take that. Yeah. So our NRE policy is such that we are not like a design house, so that we would live by NRE. So if we live by, make our money by manufacturing antennas and selling them in mass production. So some cases, if it's like let's say a simple like a matching optimization or layout review, we normally do it free of charge. But if we need to run like a more extensive simulation study, like for that solar panel example or something like that, then there is typically some small NRE involved. So it depends. If it's easy one, typically no NRE, but if it takes more involvement at time, then there may be. Or if the quantities and the potential revenue is very, very high, then maybe we don't charge anything and do it free of charge and then enjoy the manufacturing quantities later on.
Okay, thank you. The next question is, what is the minimum project volume to have access to Yageo support in breaks, hardware review, and antenna tuning?
I can take that one too. So already partly explained that on my previous answer. So typically this kind of matching circuit checking layout reviews, they are free of charge practically for any quantity, especially if it's related to the using off-the-shelf antenna, so that there is no need to kind of redesign anything. And even for like a small volume or small quantity projects, we can do like a couple of days FA work, typically say 2K USD, 3K USD, depending on how much testing or simulation is needed. So I think we are quite low entry level for giving support.
Okay, thank you. The next question is, what challenges does designing antennas for ultra-wideband create?
That falls to me again. Sorry, Gregory. I take all the questions. Challenge is the high frequency, meaning short wavelength. So all the dimensions get tiny, and especially with the embedded antennas inside the device, the mechanics affecting the antenna is a quite big factor. So need to understand all the nearby elements and that kind of things. They also affect the radiation patterns, which I mentioned on the last example, that if you want to get really like omni pattern equal per almost all directions, you carefully need to select the position of your antenna. And
Okay,
also this kind of hand effect things. If it's like a wristwatch type device, how the human body affects the antenna is also quite big.
Okay, thanks. Now maybe a question for Gregory. Back to LoRa. Do any of your multi-port products focus on the LoRa bands?
That's a good question. I don't think I could say that we really have multi-band products focusing on LoRa, as it were. For the most part, instead, they'll probably have cellular coverage. And I mentioned earlier in the slides that cellular antenna can really be used for LoRa. It covers the same. It includes that spectrum. And typically, you don't need a high gain LoRa antenna, as in you don't need to design for a very high gain 5 dBi maybe. Omnidirectional LoRa antenna base station. You might use it for a base station, but for example, with a multi-port antenna, you're probably quite happy with that 2 dBi that you might get using the cellular element, to be honest. And it's also low power, so you don't have to worry about it being too much power for the antenna to handle, depending on how the antenna is designed. If it's got elements like capacitors inside, so. Not really a focus from the multi-port antennas that are, our vehicle antennas for that. But if it's a multi-port panel antenna, for example, we do have some multi-port directional panel antennas that are in building that focus more on that spectrum, especially for public safety reasons. But I think probably multi-port usually means the cellular, Wi-Fi, that kind of antenna you might see. And so those mostly, I would say, are cellular or Wi-Fi, so not ISM focused, but it can be utilized. It can definitely be utilized for LoRa.
Okay, thank you.
So I think to summarize, so even though that antenna datasheet brochure doesn't mention LoRa, it could be used for LoRa quite well if the frequencies covers.
Okay, great. The last question I see is, do you have any panel antennas for the LoRa bands?
Oh, look at that. So the answer is yeah. We do actually. We didn't showcase panels here. It doesn't maybe come up as often in LoRa, but we do have some directional panel antennas that can work well with the LoRa band. Both some that were cellular antennas and some that are more focused that were on public safety, which means they were focused on the 700, 800, 900 megahertz spectrum, and even down to UHF. So, for example, we have panel antennas that cover 433 megahertz and 868 megahertz. That would be great for panel antenna deployment in EU, for example. So we do have some. Yes, if you have any questions about those particular products, please do let myself and Kimmo know, and we can help direct you to the right panel.
Okay, thank you very much. These are all questions for now. If you have any questions afterwards, you can always reach out to us and we will, of course, answer it. Just a few slides from my side at the end. I will share my screen again. Yes, if you want more information, you can check out our rutronik.com webpage, also our Rutronik 24 shop and our Rutronik tech site. Also, you can follow us on social media on LinkedIn, Facebook, Instagram, and YouTube, so you're always up to date and don't miss any information. If you have further questions, as I told, you can always get in touch with us. You can find my contact information on the left side. And of course, you can always reach out to your local Rutronik manager or fill out a contact form. You can find it on the right side or on the rutronik.com webpage. This was our last webinar of our ultra-wideband and LoRa series. Don't miss the opportunity to check out our Bluetooth session. It begins on the 4th of November until 8th of November. Here we have our suppliers Panasonic, Minu, Nordic Semiconductor, Kyocera AVX, Inside Zip, and Infineon on board. So stay tuned. At the end, thank you very much, Gregory and Kimmo, for your presentation. Thank you, everyone, for your participation. I hope you learned a bit new, and I wish you all a great day. And as weekend is getting sooner, I wish you all a great weekend and have a great day. Thank you, everyone.
Thank you, Tobias.
Everyone, thank you, Tobias.
Bye.
Bye.